All right, so today we're going to be talking about the end behaviors of polynomial graphs. Now, this particular graph is for x squared. It is a quadratic, so we're not surprised to see this parabolic shape here. And if I were to describe its end behaviors, I'd be looking for what happens as x gets smaller and smaller and smaller as it goes towards negative infinity, and what it looks like as x gets bigger and bigger and bigger as it goes towards positive infinity. So writing it by hand, it would look like this. As x approaches negative infinity, f of x approaches positive infinity. As x gets smaller and smaller and smaller here in the negatives, my y value, my f of x value, keeps getting bigger. As x goes towards positive infinity, f of x is also going up towards positive infinity. Now, in the video here, to improve my horrible handwriting there, I used this arrow icon for the arrow, and I used this chain link here for infinity because I had no way of typing those two things. So the arrow means an arrow here, the chain link here means infinity. Yeah. Here we have the function f of x is equal to x cubed.
Cube root function.
Not cube root, but cube function. And we got the normal graph like this. Now remember, x cubed functions, when we have nothing out of the end here, the x cubed function could end up being like this if we had something like a plus x squared or something else added onto that. We could end up getting this dip in the center here. You could end up with a double bump like that. But this is what it looks like here. For that x cubed, you're going to have, as x gets closer to infinity, f of x is also going to go to positive infinity. It's going to increase. It's going to continue increasing. On the negative side, as x approaches negative infinity, notice how it goes down. X is going to decrease. F of x is going to decrease to a negative infinity. And that's true whether when you have x cubed or x cubed plus x squared or x cubed plus x squared plus 2. Any kind of x cubed, that's what the graph's generally going to look like. It may end up with a double bump here, but it's going to get larger in the positives and get smaller in the negatives. Okay. All right, now here we have a graph of x to the fourth power, and this time I did add on some x cubed and an x on here so you can see the different curves that would happen with this. All right, but when you have x to the fourth, you're generally going to have the end patterns of x. As x increases, as it heads towards positive infinity, f of x will also become much larger, increase to infinity. As negative x, as x approaches negative infinity, f of x will still approach positive infinity. It's going to keep increasing in that side there. Kind of like our x squared graph, right?
Yeah. Yeah.
Now, one thing I did forget to mention is when you were doing the x squared, I said it was going to be positive in these directions. But what happens if the coefficient in front of the x squared was negative? Flip it upside down, right? So then both things would become negative. Let's take a look at this next screen here. I took this x to the fourth and I made it negative and it flipped it upside down. Just like it would if we had done the x squared upside down, would have flipped it upside down like that, right? So notice when it flipped upside down, we still had, but when x approaches negative infinity, instead of it going to positive infinity, it's now going to negative infinity on this side. As x approaches infinity, f of x goes to negative infinity on this side. It changes it. The coefficient in front becoming negative changes to the opposite of the pattern that you had before. And that's going to be true whether you have an x cubed, x to the fifth, x to the seventh. The coefficient in front of the highest exponent x there is going to determine whether you have it facing upwards or downwards. It's going to change the end. It's going to change that end behavior to the opposites. Before I did this, they were both positive. They're both going up to the positive. Now when I put the negative in front, it's both negative infinity. Okay, here we have an x to the 5th power. I know it's hard to see that 5 there, but this is an x to the 5th power. And again, I added on some stuff to add in those extra curves you might see on here. When we have f of x to the 5th, we'll see that as x approaches negative infinity, f of x is going to continue decreasing. So it's going to go towards negative infinity. As x approaches positive infinity, f of x is going to keep getting larger. It's going to approach positive infinity. Here I did the negative coefficient on that same graph here. Notice how when I also changed this from a negative 4x to a positive 4x here. When I changed it, I added them instead of subtracting. So I got the same exact graph, but it got flipped upside down. So I had to multiply everything by the negative. But as long as the coefficient in front of the x to the 5th is negative, you are going to have the behavior of, as x approaches negative infinity, f of x will approach positive infinity. As x approaches positive infinity, f of x is going to approach negative infinity. It switches the end behavior by having the coefficient in front of the x being a negative. Okay, in the end, you'll notice there's been a trend here. When we had even exponents as the largest exponent and a positive leading coefficient, both sides are going to go to positive infinity. Just like the quadratic graph, it would be like that. When you had even exponent on the largest exponent was an even exponent and a negative leading coefficient, both sides went off to negative infinity. Both sides decreased, kind of like the quadratic going like this. Both sides would end up decreasing. When you have an odd exponent and a positive leading coefficient, it means the end behavior is going to be positive infinity on the positive side, and it's going to stretch to negative infinity or decrease on the negative side. If you go back to linear functions, when you had a positive slope like this, it would go to positive infinity on this side and negative infinity on this side. Decreasing on this side over here, increasing on this side over here. Same thing's true when you had x to the 3rd. You had something that looks like this, decreasing on this side, increasing on that side. When you have odd exponents and a negative leading coefficient, that would flip these graphs, which would also flip the behaviors of the ends. So it goes to negative infinity on the positive side and trends towards positive infinity on the negative side. So if we're talking about a linear function goes down to negative infinity down this side, up to positive infinity on that side. Looking at the x cubed, if I had a negative coefficient on the x cubed, it would look something like this, where it would go to negative infinity on this side and to positive infinity on this side, the opposite of what it was when we had a positive coefficient. An even exponent would mean like you have, an example of an even exponent would be x squared, x to the 4th, x to the 6th. If you had the largest exponent was an even number, that's what I mean by even exponent. If the largest exponent is an odd number like 5 or 7 or 9, any one of those being the largest exponent on the variable, it's going to result in this behavior. That's the odd exponent there. Does that help? Okay. When I have a linear graph, The function of a linear graph is going to be that in the form of the mx plus b. So the exponent on this would be a 1, right? So if I have something like this, the exponent is a 1. How many curves do you see in that graph? None. Now, when we had a quadratic, we had something like x squared there, or the ax squared plus bx plus c. We had the general form was that parabola. How many curves would we have in that? Just the one curve. The exponent of 1, we had 0 curves. Exponent of 2, we had 1 curve. It never curved more than once. Remember, it's always a parabola, no matter what the adding and subtracting here is. Right, Jonathan?
Oh, yes, Jonathan. Yeah, Xander.
Shh. When we had x cubed, this is being... When we have f of x is equal to x cubed, now this is the just x cubed function, but when I start adding in an x squared or 2x or something like that, I told you the graph might end up having that double bump, right? So this could have 1, 2 curves, and the exponent was a 3. What do you think? How many curves do you think you could have for f of x is x to the 4th? The 4th power could end up looking like this, when you have 1, 2, 3 curves. So as Joseph was just saying there, which I didn't record, the number of curves is the exponent, the highest exponent, minus 1. Now that's the greatest number of curves. Do you have to have that number of curves in it? Well, with the x cubed, when we have just plain x cubed, there was only the 1 curve. It was not until you added this stuff that you started getting that double bump there. So the max number of curves is going to be the largest exponent minus 1. Okay, now you got to work with that to do your rough sketches of graphs based on the function you're given.